Me. Good afternoon, fancy meat computers. How's everybody doing? All 6 of you. 7 of you. Oh, there we go. I'm assuming that it's midterm week for everyone, including you guys. Any midterms today? Any horrible, awesome, amazing, terrible opportunities to demonstrate your learning? Making idle chit-chat while he pulls up the slides. Lambda calculus. Oh yeah, we hadn't got into... I remember this. We had not quite started church numerals. Wow. There we go. Any midterms in the chat? No, I wouldn't give you a midterm through the chat. That would just be cruel. Although I suppose I could do, now that they have the polling feature. So all your midterms are after the break. Including mine. Not immediately. Let me check. Let me check to see where we are. Okay. You. I love to see that Moonstar is using the most formal form of address. Can we quickly review Lambda trees and talk about Project 1 Part 3? Confused a bit on the first and a lot on the second. Yeah, we can... Yep, we can... Oh, yep, we can talk about that. So, so with respect to announcements, I have a couple. Number one, I found a video that's very... I might have said this already, but if you're having some difficulty, like, getting started with Project 1, this video will be very, very helpful. Because this, like, the first 3 to 4 minutes of this video is basically, like, doing the assignment in a very, like, a very, very small... Or the project, a very, very small nugget of the core ideas of the project are expressed in that video very succinctly. So I recommend watching the first 3 to 4 minutes of it. Don't worry about the rest of it. Unless you're interested in monads. Yep. Other than that, assignment 5 is now out. But yeah. No hay or anything, yeah. Hay is something horses eat. So, talk quickly about lambda trees. Okay. So, lambda trees are basically just syntax trees, right? So, you know, you take... So, basically, you know, the way that you interpret a lambda expression, you can think of that as being a tree, right? Like, this lambda applies to everything inside of it, so that's like the outermost term. The next outermost term is the y the lambda here containing y, so that's the next term in the tree. What's the next, you know, what's the next outermost thing, right? Well, in this case, you would be applying x to the result of xy, right? And then the outermost thing the innermost thing is applying x to y, right? You have to have the result of x. You have to have the result of y applied to x before you can apply x to that. That's why this is the inner bit, and x applied to that is the outer bit. So it proceeds in order of like innerness versus outerness. But if you sort of conceptually understand the structure of these things, yes. Moonstar says, I was looking at A4 Part 1 and I'm getting confused on the ordering and everything. Maybe work overload. Yeah, because I thought that was like a really easy question, to be honest. That was like... My intention was for you guys to like do it on paper and then use Dot to make a like a graph viz version. But, you know, or some other like diagram making thing. Graph viz is super, super easy though. But yeah, the assignment for... Yeah, it's like, what's the outermost... Like, start with the outermost things, peel them off, put them into the tree, all that kind of thing. But yeah, so that's that. Okay, so we're going to talk about the project for a little bit. Just a small amount of time, hopefully. So, Project 1. For Part 1, do we just copy the code from UAE1 to UAE2.hs and so on? Yeah, that's the intention, is like UAE2 is going to require the stuff from UAE1, so it's like, take this, yeah, it's you copy it and then you make modifications to it to get the next iteration. Why not let you use ticks? By giving bonus marks on GraphViz, you made me want to go mad attempting it in org mode. Because GraphViz is a lot better than ticks. It's a lot better than ticks. Specifically, like, it has its domain of applicability, right? Like, it's really good for doing, like, these types of directed graphs. Like, it's made specifically to be able to do graphs. Like, directed graphs are what Dot in particular of the GraphViz package is made for. So you will not find, like, once you've tried it, you'll be hooked and you will never use ticks again for the same sort of thing. Ticks is okay for like you can do graphs and graphs in the statistical sense. But if you're doing graphs in the computer science sense, use Dot. It's much easier. Much easier. But of course, I don't think it integrates into org mode without some, without the hammer of justice. So, yeah, just, it's a bonus mark. You don't have to get it if you don't want it. Yeah. Does lambda x go like lambda apply x? No. So lambda, like a lambda abstraction and the application of, like the application is a separate type of term in lambda calculus, right? So it doesn't really make sense to say lambda apply x. It's like lambda x extracts x from a term, and you can apply some other, term y to that. So, like, if anything, lambda apply would be the evaluation, right? You would lambda apply in order to evaluate, but I don't like that terminology, so don't use it. Do we have enough info to do part P1 question 3. I didn't recognize the syntax for big step. I may have missed it the lecture when we did this. No, we didn't do big step in lecture. I assumed that you could look at these as rules of, rules of evaluation and encode them. So, very roughly speaking, a value evaluates to itself. If T1, then T2, else T3, that will evaluate to value 2. If T1 evaluates to true and T2 evaluates to value 2, right? Same thing for false, with T3 evaluating to value 3, right? T1 evaluates to numeric value 1 when successor of T1 evaluates to successor of a numeric value 1, right? So that's a congruence rule. If T1 evaluates to 0, then pred T1 evaluates to 0. And so on and so forth. So you'll notice that I have something that looks like a determinacy rule written here. I'm not asking for a proof of that. This is just you can use this for debugging. This is a fancy way of saying that any of the terms that you used to debug your multi-step semantics in part 1.3, those same test cases can be used to debug your big step semantics, because everything should hypothetically evaluate to the same to the same thing. So yeah, it's all right. You want to know the big secret? The big secret is you evaluate these guys first, right? It's like the difference between big step semantics and single step semantics when you do an actual Haskell implementation is that in the big step semantics, you jump to the result rather than in order to solve if T1 then in order to solve an if then else, you don't just need T1 evaluating to either true or false. You need, and eventually evaluating to true or false. You need whatever the results, the evaluation results of either T2 or T3 as well, and then you perform the whole substitution. That's the big step semantics. You'll notice there's no congruence rule on if anymore. We don't have the rule T1 evaluates to T1 prime, therefore if T1 evaluates to if T1 prime. We don't have that anymore because we don't need it. Because if T1 evaluates true and T2, then you can just, you can, programmatically, you can then proceed to calculate T2, what that evaluates to. And of course, because it's Haskell and it's a lazy evaluation, you can actually put T2 and T3 both in a where clause, and it'll just use the one, it'll only evaluate the one that's used. So that's lazy evaluation for you. So yeah, it's this is an extension of your knowledge of single-step semantics, but it should be very reasonable for you to implement it. It's you can literally take the single-step semantics, copy the function down, change the names, modify some things, and that's this question done. Let's see. For Project 1, are 1.2 and 1.3 supposed to go in UAE 1 or UAE 2? So Part 1 goes in UAE 1, Part 2 goes in UAE 2, Part 3 goes in UAE 3. Well, Moonstar, maybe if you want to drop by office hours on Thursday, we can take a look at how you're doing it. I'm trying to ask what is the AST of lambda x dot y. Oh, okay. Yeah, I can. Yeah, I can show you that. Absolutely. It's very simple. So lambda x, I'm just going to use slash for lambda, x dot y, that would be lambda x y. That's the syntax tree right there. Ta-da! So it's recursive on itself and will eventually be kind of small step, etc. Well, I mean, it is recursive on itself, yes. That's, yeah. Actually, now that you mention it, that is the primary difference between big step and small step, is that big step, in big step, it calls other things recursively, which you do to a certain extent in small step. Like, you have to do that. You have to step into T1 to get T1 prime, but you only do it for one step, right? In big step, you don't need an evaluation, like a multi-step evaluation relation. Big step does all of the evaluations shunk all at once. One call. For part 3 is more of an issue of coding, not semantics. Question. For the if-then-else syntax, I see the sample text case uses if-then-else term instead of if term, then term, else term. Is that the syntax you should use? Well, let me just pull it up here. That's how it would look in Haskell. I am 100% okay with you guys using if-then-else as a prefix operator and not a mix-fix operator. In the notes, it's been a mix-fix operator because that makes sense, but in Haskell, it's much easier to do it as a prefix operator, so I would recommend doing it as a prefix operator, not a mix-fix operator, because that just makes your life way too complicated. The reason it's written like this, and like the dollar signs here, those are also Haskell syntax, right? It's like a way of avoiding all of these parentheses. If you include a dollar sign in Haskell, that means open parenthesis, close parenthesis at the end of the line. It's a more technical way of saying it is that you're reversing the associativity of the function application, which is implicit in the spaces. But yes. Issue: when you can't attend single office hour of any class due to conflicts. Really? You can't make either of the 2 office hours I have on Thursdays? There's no apply in the middle. In comparison, what's the AST of lambda x.xy? Is that an actual assignment question? Because if that's an assignment question, I'm not going to give you the answer. Because that would be giving you the answer to an assignment, which, you know, the whole point of the assignment is that you figure out the assignment. Let's see. Nope, okay, we're clear. So, if you had x.x and then you apply y to it, then that would be apply left, right, lambda x, x, y. That's how that would work. You weren't saying why? Okay. Well, if then shoot me an email and we'll have a quick Teams call or something. I'll help you out with it. Incidentally, office hours are electronic as well, so if it's that you actually have class between 1:30 and 3:30 on Thursday, then, you know, we can arrange another time. For sure. Cool. Alright. So, time to keep going. It's well time for us to keep going, actually. So, let's get back into our lecture material. Let's talk about church numerals. So, remember last time we were doing church booleans. And, you know, we defined true and false. We defined a function that tests this, although it's trivial. We defined an AND operation, and we defined what a pair is. Pairs are going to become important later on. They're not going to be important yet, but when we start, like when we get into topic 6, we're going to see pairs come up again. But yeah, so let's talk about church numerals. So, we can define the natural numbers in lambda calculus in a manner still quite similar to piano arithmetic. So you can already, I hope, recognize that the structure of this should be structurally reminiscent of the successor chains we used to represent the natural numbers in UAE. So, C0 is lambda s lambda z z. C1 is lambda s lambda z s z. C2 is ss z. C3 is sss z. Notice that we're having to put these parentheses in here because the way that these are getting applied, for each new term that we're adding here, we're applying everything before to it, right? We're sort of reversing the associativity of function application by using parentheses. You know, we wouldn't have to use the parentheses if we were doing right associative instead of left associative, but, you know, it would be very confusing for us to have lambda calculus be left associative on one slide, right associative on another slide, so hence all of the parentheses, even though the parentheses are going to be a bit of a pain. So, in other words, church numerals take two arguments, a successor s and a zero term z, although, you know, in lambda calculus, these things do not have semantic content. Like s and z do not have semantic content until something is applied to the function, and that gives them a function itself, so that gives it the semantic content. By the way, I'm trying the low latency. So just to check the latency, when I clap, could a few people in the chat please type clap as soon as they see me clap here? Okay? I just want to check the latency. How is that? How's the latency on that? 4, 5, 6, 7, 10. Ah! That's like 1/3 the latency we usually have. That's really good. Yeah, I think I'll... And the quality's still good, eh? Have you guys noticed a quality... Like, have we taken too deep a hit on quality here? Or is it, like, about the same as it was before? Very cool. Very cool. Wonderful. I think I'll keep doing the low latency then. I'm not gonna do the ultra low latency, although I suppose we could try it. But the problem is once you set it for a stream, you're stuck with it. So full screen, yes. Sorry. So here we go. Z is applied to S, and the result is applied to another S, and so on until we reach N applications. So the thing that makes, church numeral C20 equal to C20 is because there are 20 function applications going on. 20 applications of Z to S. So, correspondence with Booleans. The observant student may have noticed that C0 has the same definition as false, right? A false is lambda t, lambda f, take f, and this is lambda s, lambda z, take z. This is sometimes called a pun in computer science because it's not funny. The same thing occurs in lower level languages where the interpretation of a sequence of bits is context dependent. In C, the bit arrangement all zeros corresponds to 0 for integers and false for booleans. And character arrays are also, if you interpret those bits as characters in a character array, then you would get 4 null characters as well. I feel like I've already done this slide, but perhaps we didn't go particularly into this. I think we may have just started the new material, but it's okay. It's fine. So, success! We can now define the successor function on church numerals as follows. The successor of some numeral n is lambda n, lambda s, lambda z, s, n, s, z. So just to prove that this works, we're going to do the successor of 2. Right? So, lambda s, lambda n, lambda s, lambda z of s, n, s, z, all of that with C2 applied. C2, oh, I need to, ooh, yeah. I've got a pen. There we go. So C2 gets applied to n. What's this? Is it 3? 3, okay. Gotta get my keys prepared. Okay, so C2 gets applied to n, right? Which yields, basically the only n is right here. So the we get lambda s, lambda z, s C2 s z, right? So we get lambda s, lambda z. We expand C2 here, right? So that's applying s and z to lambda s, lambda z, s, s, z. So you can see where we're going here, right? S gets applied, and it just replaces s with s, which means that there's no replacement actually. Same thing happens with z. So we have lambda z, s, s, z. So z gets replaced with z, which is no replacement at all. So we get s, 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 z, which is C3, which is correct. Successor works! Fantastic. So let's talk about addition. Similarly, we can apply addition as follows. You'll notice that there's a fair correspondence between successor and addition. With addition, we're adding lambda m, and basically what was the successor function now gets applied to m here. So let's do 2 plus 2, right? So we've got lambda m, n, s, and z, m, s, n, s, z, c2, c2, right? So we take the first c2, and we apply it to m. So we put it here, right? So this is fine. This works. Next, we take the next c2, and apply it to n. So that replaces this n with C2, which is what we see here. We then have, now we're out of easy ones, right? So we now expand our definitions of C2. Now, we could have expanded them one at a time, but I decided to expand them both at the same time. It's the same thing. Technically speaking, expansion isn't an evaluation step in our calculus, but I'm going to be considering it an evaluation step in the calculus because when it comes to practically doing the evaluation, it is a step for us while evaluating, even if the semantic doesn't consider it to be a step. So I'm considering it a step here. So we expand. That gives us these guys, which are the definitions of C2 in here. We then take a look at the first one. You can see we've got S applied to lambda S, lambda Z, S, S, Z, which, of course, yields lambda Z, S, S, Z. We then deal with this next lambda, lambda Z, and we apply the following argument to it, which is all of this stuff. So that gets thrown in. So we end up with SS, lambda S, lambda Z, S, S, Z, S, S, Z, which you can kind of see where this is going. We apply S to lambda S, we apply Z to lambda Z, bing, bang, boom. We result in SSSSZ, which, of course, excuse me, is our definition for C4. Any questions? Is this making sense? Is this making sense? Question. How is this the definition of C4? Well, if you take a look at the definitions here, you see, like I said, ... because, you know, this pattern extends to all of the rest of the church numerals, right? So if C0 is 0 applications to S, C1 is 1, C2 is 2, C3 is 3, then it is logical to infer that 1, 2, 3, 4 is 4. You might also say, perhaps I have a mismatched bracket somewhere. But yeah, I think I've got one pair of brackets too many that I held. But yeah. Like this outermost pair of brackets is redundant, right? Because like it's like single term inside of a bracket means the brackets are redundant. So far about 80%, I'm assuming people who said dollars are fine. So 80% of the class is okie dokie. Okay. Moving right along then. So the next derivation gets a little bit longer. Let's do multiplication. Times have changed. Finally, let's define a multiplication operator. So you'll notice that multiplication is here being defined in terms of, like, we're using the definition of plus in order to do the definition of multiplication, which, you know, makes a lot of sense intuitively from our early elementary school understanding of what multiplication is. But up to this point, we haven't really had to use an operator within it like that. But you know, that's how we're gonna roll for this one. So let's do 3 times 2. So, times C3, C2. Oh, I didn't actually tell you what... No, yeah, I did. So it's lambda m, lambda n, m, you apply plus n, and then to that you apply C0. So let's apply C3 and C2 to our times function. So first one, of course, C3, we're going to... I think I'm going to stick to underlining instead of circling. I think it works better. We're going to apply C3 to m, which replaces it here. You'll see there. Right? Same thing with C2. C2 gets applied here because of its lambda n. So there we go. It looks like I have decided to expand C3 at the same time. Probably should have put that on a different line, but, you know. So that results... once I evaluate C2... Once I evaluate C3... F6 mode 3. There... F6 3. There we go. Once I've done this substitution, I just sort of get rid of these brackets. Right? Because they're not needed anymore. And I've expanded the definition of C3, which is lambda s, lambda z, s, 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 z. And then that we are applying plus C2 to that, and C0 to that as well. Can we petition me to color code my line-by-line steps like this? Oh, that's so much work, though. And besides, like, if we were in class, I would be doing this on a chalkboard, so... But anyway, so, this is two applications at once, right? So I'm applying plus C2 to S, and I'm applying C0 to Z. So C0 goes where the Z is, plus C2 goes where every S is. So we got 3 plus C2s applied to C0. What is the use of having C0? You will see, my friend, you will see, so to speak. That's a pun. So I don't know why I don't know how I highlighted that permanently. I don't know. Anyway, is there anything in LaTeX you can color the brackets by layer? You can definitely put in like manual coloration commands in LaTeX. It's just a pain in the butt. That's all. So a question: why not prove this by saying C2 plus saying plus C2 C0 is C? Since plus works, or does it? We only showed that it worked for a specific example. Yeah, so not automatically. I'd have to do it by hand. So somebody was asking about this with the with respect to the first. Somebody was asking about this with respect to the A4 as well, and so no, you don't get to assume that plus works. Because assuming that plus works would mean adding plus as a term of lambda calculus with its own evaluation rules, and right now we are working in the pure lambda calculus. As you're going to see, once we get into topic 6, reasonably early on in topic 6, we're going to show how one goes about enriching the lambda calculus with, things like the types of operators that you would expect to exist, like addition and multiplication. That's not the point of this. The point of this is to demonstrate that every one of these steps can be done in pure lambda calculus, right? With no reference whatsoever to any semantic that's external to lambda calculus. And, you know, to use the observation that, you know, C2 plus C2 evaluates to C2, it's like, you know, like we would be able to use that once maybe in this evaluation, maybe, you know, but, you know, it's... The point of this is that we're doing everything via the substitution operation, which is the only semantic operation that we have available to us in the pure lambda calculus. But so one of your colleagues asks me to explain this bottom step again. Yeah, so I'm just applying. I'm doing two at once, right? So first I apply plus, so every s gets replaced with a plus. That's all of these guys, and you get rid of this guy because he's done, right? Then you take C0, apply it everywhere you get a z, get rid of the z, and then get rid of the braces, and a brace here, brace there, and this is what you're left with. Okay? Yeah. Yeah, these things are going to get kind of long if I can't do multiple operations per line. But yeah, good. Cool. So, subderivation. Technically, this is cheating, since we don't have a rule for this type of substitution in the semantic, and it violates our evaluation strategy, but this is going to save a lot of time. It'll save us 3 repetitions of the same derivation. You know I just said that, you know, why can't we just say plus is, you know, see, like, why can't we just say 2 plus 2 is 4? And it's because we don't have a concept of 2 or a concept of plus, you know? Because lambda calculus lacks, like, it doesn't exist semantically like that. But I am going to use plus C2 evaluates to this other lambda expression and then sub that in a few times, because that'll save us time and space. So, plus C2, that's, here it is, lambda n m n s z, ms ns z, which we are applying lambda s lambda z ss z to. So we replace this guy in for the s, or sorry, for the m. So it gets here, strike that out, and replace it here. So that's the next line. We then these last brackets are redundant, of course. We can apply the next argument. We have no more arguments to supply here at this level, so the next level we can get to is here. We're going to apply s to s, so s gets x'd out. We're replacing s with s, which of course doesn't do anything. And of course, the next thing we're going to do is apply NSZ to Z. So what we end up with as a result is lambda n, lambda s, lambda z, s, s, NSZ. So there you go. So we're going to take this and we're going to sub it in a few times. Ta-da! So, I'm using a squiggly arrow to indicate that I'm doing, like, this guy, this substitution. So plus, 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 C0. We get, the first thing we do is we expand the first definition of plus, right? So you'll notice, once we've done that, this is one term here, right? So this gets substituted in where n is, n being right here. Cross out n. This is the substituting thing. So this is what we result in. It's SS plus C2 plus C through C plus C2 plus C2 C0 SZ. Right? That's as far as we can go without further expansion. So we expand. We expand this instance of S2, or plus C2. Right? This guy here. We're now, so we've expanded that. We have performed pretty much the same operation. You'll notice that this guy up until here is all one term. So we apply that where n is. That's right here. And then we get as a result lambda z ss and then plus c2 c0 sz. So this is the term that we substituted in. Did I make a plus command or something to avoid typing this so many times? No, if you take a look at the LaTeX source for this, you'll see that I didn't use any fancy commands. I actually did this by hand, thank you. Because I don't expect you to do anything that I would be unwilling to do myself. Because that's not a good quality, like that's not leadership. A good leader will never expect anything of anybody that he isn't willing to do himself. Or herself. So there we go. So we've got this lambda z that's left over, but you'll notice we've got a z here, right? So we just apply that, and z, applying that just leaves us with the z, replaced for itself, so that's fine. Right? Oh, it looks like I'm applying two things here. Yeah. So this guy right here. Doop. Here. Sorry, this is not as easy in a wrist brace. So that gets applied to n. S gets applied to S, so that disappears. Z gets applied to Z. For some reason, I did these on different. I did the Z on a different line. Not sure why. Probably because I was, who knows what I was doing at the time. So that simplifies out to lambda S, lambda Z, SS, SS, plus C2, C0, SZ. Now this is something, we should recognize the pattern by now. So we expand plus, bloop, right? So we first apply C0. It gets replaced. C0 replaces n, right? So there you go. Next thing, we apply S to S and Z to Z. Or I guess we're doing these on separate lines this time. Yeah, so S gets applied to lambda S. So that is fine. That just cancels out. Z gets applied to lambda Z. That's okay. That just gets canceled out. Right? So we are left with SS, 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 C0, SS, Z. C0 is, of course, lambda S, lambda Z, Z, right? So you take the first, and it just gets dropped, just like with false. You apply Z. All you have left is an identity function, essentially. So you get SSSS, SSSS, Z, which I'm sure the more observant of you will have noticed that that is the exact same thing as C6. So we may conclude that times applied to C3, C2 does in fact yield C6. So multiplication works. Ta-da! Yes. Parentheses equals squiggly eye face. Yes, absolutely. You'll find when programming in Haskell and in lambda calculus that you are swiftly thrust into parenthesis hell. But yes. So, Um, so, one of your colleagues thinks that me going through this with you in an algebraic sense is meaningless, I guess. I think it's meaningless to explain the concept algebraically, analyzing line by line. A better understanding can be, for example, NVSZ gets rid of its value constructor. Um, well, when you get to grad school and when you get to doing your PhD and when you get to teach this course, you can teach it how you like. But while I'm teaching it, I'll teach it how I like. And that's all we got for today. So there you go. Any questions? Thanks for making A4 due October 14th. Did I do that? I think I did that. It's hard to keep track of the classes when you're teaching 3 of them. Assignments. Up, 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 up. Oh yeah, there you go. A4, October 17th. There you go. A4 is due October 17th, which means you have reading week to work on it. So, there we go. So, the curly symbol means the substitution. Yeah, I'm using the curly arrow to be like, this is like not, like this is many evaluation steps, you know? Like basically I'm wrapping up all 4 of these evaluation steps into one, so, yeah. In the next slide set, I get like a slightly more rigorous, I figure out that I can like put multiple arrows to indicate multiple evaluation steps instead of one. And so the next, I think I got better at like writing this down as it went on. But yeah. Yeah. Oh, by the way, is it okay for you to get something like numeric value 0 from P1 part 1? Yeah, it depends on whether you nest the it depends on whether you nest the booleans or nest the natural values within or the numeric values within the regular values. When I did it, to be completely honest with you, I kind of made 2 subtypes, but the like values didn't inherit from like the values didn't have numeric values as a subtype when I did it, which, you know, it really only it's only a syntactic difference really, but like I was like, well, booleans have their category, numeric values have their category, you know, but yeah, it's with numeric values as a subtype of values, and values being a subtype of terms, then yeah, you exactly would get numeric value 0. Yes, absolutely, that would be correct. Yeah. Yeah, I realize that you know, this has been a semester where like perhaps there have been more corrections and such than you would typically see, but, you know, the, it's sort of a natural consequence of all of the, content for the course being generated, you know, concurrently with its being, you know, produced. So, you know, there are, you know, I don't know the degree to which, you know, these sorts of corrections are issued in other courses, but, you know, I know that, you know, there's only so good I'm only so good at this, and I can only, you know, produce content at the pace that I have to produce it at, with like a certain level of, you know, correctness. I can't catch every error that I make, unfortunately. So I appreciate that when people point them out to me, and I will do my best to try to correct them as they come up. But, you know, it's pretty rare for a course to be like done in this manner. You know, normally you don't take the very first. Normally, if you're taking any particular course, it's not the first time, you know, for that material is being run, which it is in this case. But so, question. So you can do it either way. Yeah, I think you could do it either way. I don't think we'll make a big. I'll tell the TAs not to grade people down if you want to do the Booleans separately and not make the numeric values a subset of the rest of the values, then that'd be fine. And if you do make them a subset, that's also fine. It's like, you know, 6 to 1, half a dozen to the other. Going to take 3DS3 in 3 minutes. Ah, good luck. Good luck on your tests. Switching to another syntax context. Yeah. Yeah, that's, what is that? Operating systems? 3DS3? It's bad when like most of the comics that I can come up with are like math is complicated type comics. It's like, haha, math is complicated. Concurrent systems. Ooh, I hate concurrent systems. Oh man. When I took concurrent systems, it was in 4th year, and it was I was taking it as a technical elective, and I was kind of disappointed because I had a professor by the name of Dr. Skip Pullman, who is unfortunately passed away, and he was like from like the old guard, and felt that, you know, in a course about concurrent systems, it was still relevant to talk about Fortran. So learning the syntax of some obscure app to make diagrams. Ah, yeah, why would you learn the syntax of an obscure app when you could learn the syntax of an app that everybody uses to make their diagrams, like GraphViz? Like, you know. Because this app does nothing but make these diagrams really badly. Yeah. I kind of, like, I think it shouldn't matter what the app is as long as the diagram is readable, you know? But that's my perspective, you know? Clearly opinion varies. But yeah. the I'll say just one more thing about like this is a lot of parentheses, right? But I'll say one more thing about it. We managed with lambda calculus to perform multiplication with only a substitution operator. Now, whether or not you think that's clumsy, it doesn't matter if it's clumsy for us, right? It doesn't matter if it's clumsy for us poor, stupid, simple humans, because what we're looking for is a operation that can be performed quickly and repetitively with little thinking, that can perform some pretty advanced mathematics. So, like, the whole point of this is that it's computation, right? Like, we're calculating by hand what the computer will do automatically because it's a computer. And, like, so yeah, it's, you know, the reason that this is a bunch of algebraic substitution is because that's the entirety of the pure lambda calculus is algebraic substitution. If you're doing anything else, then you're adding semantics to it that aren't in it, right? So, yeah. There's nothing to the course except the app. They auto-rename state names with numbers and mix the order. What? What? That just doesn't make any sense. Well, enjoy concurrent systems. I'm gonna log off here, folks. Take her easy. I'll see you guys tomorrow. Try not to die from your midterms.